Welcome everybody to the first day of Qt Developer Days 2009. My name is Alan Izust, and I'll be giving you a shortened version of our training material. Just a little preface. The full version has at least maybe twice as much material as what you're having here, but we couldn't fit it all into 1 hour. So I'll be skipping around a little bit. But if you want the full version of the course, you should sign up. Just a little introduction of myself. We've all heard about what ICS is. That's the company that I work for. We're the North American training and consulting partner of Qt Software. I've been working for ICS for almost 2 years now. I wrote a book on Qt4 called Introduction to Design Patterns in C++ and Qt4. And I've also written a training course on Frog Logic Squish for Qt developers in Python. I'll be teaching that on Thursday and Friday down in Mountain View as an open enrollment course. So, now we're going to talk about graphics view. In this course, we'll give you an overview of differences between, say, a painting, low-level API, and a structured drawing API. We'll show you how to use the graphics view framework. We'll give you an overview of the architecture. What are the main components of this API? Scenes, views, items. We'll talk about coordinate systems and transformations and how they can be used. We'll show you how to extend graphics items. Let's say that you want a graphical thing that doesn't already exist and you'd like to design it yourself. How would you do that? How would you add it to your scene? How would you create a scene, organizing your items? How do you display them with views? And we'll talk about collision detection. So a painting, when we say we're painting, we're talking about a lower level of work. We're dealing with primitive graphics, pixels, colors, QPen, QBrush. Adobe Photoshop and GIMP are examples of painting applications. And QPainter is an example of a painting API. When we're talking about drawing, we are talking about a higher level where we're drawing structures, things that are complicated. And the idea is that we want to be able to reuse these items. So Adobe Illustrator and Umbrella would be examples of drawing applications, and QGraphics View would be an example of a drawing API. So, it's a structured graphics interface. It is object-oriented, so components can have an inheritance hierarchy. It supports the composite composition design pattern where you can build up more complicated things from simpler components. And it permits you to manipulate these items, moving, transforming, stacking them on top of each other. And we'll show you how to do those. One example of an application that uses the graphics view is the KDE 4 Plasma Desktop. This is the next generation of Linux desktops, all written in Qt. Graphics view was introduced in version 4.2 of Qt. It uses the model view controller paradigm in the sense that you can have multiple views of the same scene. And they don't even have to show you the exact same image. One view could be zoomed in, whereas another view might be zoomed out or showing you a different viewport. The Graphics View API allows you to very efficiently manage large numbers of graphics items. And It's also designed to be able to perform hit tests and collision detection very quickly. It propagates events from the scene down to the items. The coordinate system is resolution independent. We're not dealing with pixels anymore. It supports animation, and in many different ways. And we'll talk about printing and rendering and some of the default behaviors for common operations that you inherit whenever you extend from the graphics item. So we'll start out by showing you a hello world. It looks a bit like the hello world that we saw earlier today with just the label on a button. But now we have a circle drawn around it, or an ellipse rather. How do we write a program that will do this? It's fairly straightforward. We create our queue application as before, and then we create a scene. And the scene is going to contain the two items that we want to show, but we're not going to see anything until we create a QGraphics view of that scene. And then we tell the view to show. So this is our Hello World application. So the QGraphics scene is what we would say a model for the QGraphics view. And the scene is a container for graphics items, and it manages them, which means that a graphics item can only belong to one scene. If you try to add it to another one, it'll get removed from the previous one. But it's one-to-many in the sense that you can have many views that show you the same scene. So the graphics scene, we say it's a container for graphic items. It handles event propagation. It manages collision detection. It supports very fast item indexing. And it handles item selection and focus. What else it does, it renders the scene onto your Paint device, handling what we call Z order to determine which items are in front of the other items. Oh, and I should mention, feel free to stop and ask questions because we're not going to run out of time. So the most important methods that you should know about the graphics scene, add item. This is how you would add a pointer to a QGraphics item. Yes? So the question was, when is the drawing actually happening? And the answer is, not until you create a view of the scene. You're not going to see anything. So up to this point, all we're doing is adding objects as sub-objects to other objects. And we're not doing any kind of graphical operations at all until we hit this point.
So it's not even drawn in the background, and you only see it when you show?
Correct. So,
If you were to update the items in that scene, when would they be repainted?
you have control over that. You can decide when or how your view is repainted, and we'll talk about that a little bit later. So, when you want to add an item to a scene, you call add item. If you want to get a list of all the items that are in it, you call items. If you want to know which ones are selected, selected items. And scene rect gives you the bounding rectangle of the entire scene. Now let's talk about the actual class called QGraphics View. There's the QGraphics View collection of classes, and then there's one class that actually has that name. And this is a scrollable widget and a viewport onto your scene. Handles zooming, rotation, other transformations. It translates input events from the view into QGraphics scene events, which of course have the different coordinate system. And so that way that's how it maps the coordinates between your scene and your viewport. It also provides level of detail information to your items. And that way you can determine as you're zooming in closer whether the smallest items need to be painted or not. And when you zoom out, you can also make those kinds of decisions. And it supports OpenGL. So you can use an OpenGL paint engine on your QGraphics view. So the important methods of QGraphics view would be set scene, so that says which scene it's going to use. Set render hints. These are more for performance reasons. You might want to enable or disable smooth pixmap transformations or anti-aliasing, depending on your platform. You can ensure that a certain point or a certain item is centered in your view. And then for mapping to and from scene coordinates, we use map from scene and map to scene. And then we have high-level transform methods, scale, rotate, and translate. These help you zoom, rotate, map over to a different coordinate system. And you can get the transformation matrix of your view at any time by just calling matrix. So the basic element that we're talking about, and for those of you that have done Qt3, we used something called a canvas back then. So that's why we're using canvas here. It is equivalent to your canvas element. It supports the parent-child hierarchy, just like QObject and QDOM node. And there are some concrete derived types. So graphics item is abstract. You have to implement certain pure virtual methods on it. But then we have concrete types for rectangles, polygons, pixmaps, texts that you can also extend or just instantiate directly. You can move, scale, or rotate them very easily with the same operations that we saw on the view. Scale, rotate, translate. Those exist on the item as well. And each item has its own local coordinate system. And it performs automatic transformations as needed. And it has drag and drop because they're movable. So you can click and drag and drop, and you don't have to write any of that code because it already works for graphics items out of the box. Thing to understand, though, is that a QGraphics item is not a widget. It is not derived from QObject, and that makes it much more lightweight. And this makes it possible for scenes to easily contain thousands of items. Another thing to keep in mind, they use a different Q event hierarchy. And this is because, primarily, that we're dealing with different coordinate systems. And the QGraphics scene event supports floating point coordinates. But there are other differences as well. Now, let's say that you did want to put one of your favorite Q widgets into a graphics scene. Maybe it has some GUI controls as well. That is possible. You can embed it in a QGraphics scene with this helper class called a QGraphics proxy widget. And that's actually covered in the full version of this course. But you can see some examples of it in the map viewer example. But the idea here is that you have your own widget. You can create a QGraphics proxy widget of that and then add the proxy widget to your scene. Even though the name of the class ends in the word widget, it's not actually a widget. So the important methods to know about for QGraphics item, we have paint, just like we do for widgets. We have bounding rect, which gives you the bounding rectangle of your thing. Shape, which is used for hits and collisions. Position, where its position is in the scene. And Z value, which is where it is in relation to other objects that are in the scene front and backwise. Yes?
Does it support animation instead of how you show the
Okay, so the question is, does it support animation? The answer is yes. There are lots of ways of doing animation on your object, on your items. Unfortunately, that's covered in the full version of this course, and we're not going to go into too much detail about it. But there are some examples that show you, and I can show you one of them if there's time.
So that means there's no easy way, like a function called beautify flag fading or...
I didn't say there's no easy way. There are lots of easy ways. The problem is there's so many different ways that we don't have enough time in this talk. So, coordinates. Like I said, if there is enough time, I will show you some of these. So, coordinates, each item has its own local coordinate system. As I said before, they're logical coordinates, not in terms of pixels. We work with floating point numbers, not integers. And furthermore, items, because they do support parent-child hierarchies, can inherit their positions and transforms from their parents, which might be other items or your scene. And the z value is relative to the parent. And an item transformation does not affect its local coordinate system. So when we're painting items, they're painted recursively from parent to children in a z value order. So here I'm just going to show you a quick little example that shows how we have parent and child items. So this is the parent item. This is, this is the child item, and this is a parent, and this is the grandparent. And as you can see, children do inherit their transformation matrices from their parents. When you rotate this, it doesn't affect the parents, but when you rotate the parents, or rescales, it does affect the child. Oh yeah, right. There's a little printing error here, so I'm going to just open up this one too. There it is. So a Q transform is a 3x3 matrix, and it describes a two-dimensional linear transformation. So we have high-level operations for translate, shear, scale, rotate, and project. And they all perform transformations from x comma y to x prime y prime. And the way that it works is with this basic formula, where they're similar to y equals mx plus b, except in an extra dimension. And then the M13 and M23 matrix items are used if we're doing perspective transformations, which are also known as affine transformations. Weird. Okay, well anyway, this is what it's supposed to be, and this is what it looks like on your slide. Sorry about that. So each component has its own coordinate system that applies to views, scenes, items, and child items. And you can always transform one component system into the other via one Q transform. We can set the transform to apply it to the entire scene or on the view, rather. This helps you for, say, resize operations or scroll bar scroll movements. And then there's a transformation anchor, which is a property to control how the view behaves when you do a transformation. So you can have the view always reposition its scroll bar so that center point is the anchor, or you can have it so that the mouse is the anchor, or there's no anchor. Now, how do we make our own custom items? Well, we have a couple choices. We could inherit directly from QGraphics item. And if we do that, then we have to implement paint, bounding rect, and optionally also shape. Or we could derive from one of the concrete types, such as polygon item or ellipse item. And we'll show you how to do both. Bounding rect has to return the minimum bounding rectangle for the item. It's used for scene indexing as well as culling. And then this is another method called shape, which actually returns bounding rect by default if you do not implement it. And this is used to determine hit tests, collisions, and so on and so forth. Say that again? Yes. It's based on your own local coordinate system, the bounding rectangle. Now, before we implement our own graphics items, we need to know a little bit about event handling for these items. And the reason is because we're going to be overriding some of the methods in order to do interesting things, and we need to know what they did before in some cases. So, first thing to note, the event handlers look a lot like the ones for QWidget, but they're not. It's a different class hierarchy. QGraphics scene drag drop event, QGraphics scene context menu event, so on and so forth. Again, these are because we're using different coordinate systems primarily. If you wanted to filter all events on a particular item, you would override this scene event method, which would be analogous to overriding the event method of a QWidget. Now, when we select or focus or move a graphics item, the actual code that implements that is in our base class event handlers. Mouse move event, mouse press event, mouse release event. So, if we are going to override any of these methods, we have to make sure that we call the base class versions as well. Otherwise, we won't be able to select, move, and focus as we were able to before. And here's a picture that just shows you what a bounding rectangle looks like in relation to the actual shape. And for elliptical shapes, we can see that sometimes the bounding rect will hit another shape even if the shape does not. The item is in complete control of drawing itself. So you can use... Sorry about that. So you can use standard QPainter drawing methods if you want when you implement that paint method. You don't draw the background. And you can make arbitrary shapes. They can be polygons, they can be curved, they can be non-contiguous. So here we have a pendulum demo. And it's a fairly simple item. It's just a line and a circle. And there are a couple of ways that we could implement this. The first one is by deriving from QGraphics item, our abstract base class, and then we implement the bounding rectangle and the paint method. So that's the minimum that you would need to do. And here's how we'd write it. So the first thing I want to mention is the bounding rectangle does need to take into account the width of your pen, because otherwise, since it's used to calculate what areas need to be repainted when you move it, if you don't, you might see little outlines left behind. The paint method, one sec. Hello, hello? Okay. The paint method, we are passed into this function a painter that we can paint with, as well as a Q style option graphics item, which gives us additional information about the level of detail and things like that. The painting that we do looks just like it would be in a paint method of our widget. So we're drawing a line, and then we're drawing an ellipse, and then we're making a nice radial gradient so that it looks pretty. We can see the radial gradient here. So that's one way of doing it. But because we happen to be composing this item based on other things which are almost primitive, we can reuse classes that were already written for us so that we can write less code ourselves. Yes?
How well does this translate performance-wise into OpenGL backend? Is that sufficient? I mean, how does it work? Does it get converted into texture, or how? The difference again back to the very beginning of your presentation between the drawing stuff like that and.
So the question is, when you, okay, the way that you can use OpenGL with Graphics View, one way, is by setting its backend painting engine to a QGL widget. So then the question is, what happens when you do that? What sort of performance improvements do you see? And I can't really answer that question because I haven't tried it myself. Is there anyone else in the room who'd like to take a stab at it? I guess you have to try it and find out. Okay, so the better approach for extending from QGraphics, well, the better approach for making a pendulum would be, instead of drawing directly with your painter, you could compose your item based on simpler items. And if you want to do that, the sensible base class to extend from would be QGraphicsItemGroup. So when you create a QGraphicsItemGroup, presumably you're going to be adding a few other items as children to this item. And here what we're doing is we're creating the rod as a graphics line item and the weight as a graphics ellipse item. And then after we create it, we can set the pens and the color at and so on and so forth. But now we don't need to implement paint because it knows how to paint itself. It just calls paint on all of its child items. Collision detection. There's a colliding mice example, by the way, that comes with Qt that you can look at that shows you the full code of these next couple of examples. But I'll just summarize. What it does is it shows you a bunch of mice running around, and then whenever they collide with each other, their ears turn color to red from green. And they also change their direction a little bit. So, to find out whether your item collides with another item, you can use collides with item or colliding items. It gives you all of the items that are colliding. The shape method is what's used for collision detection. And the items returns all the items found in your polygon. So items takes a polygon and gives you just those items that are in it. But of course, the way it calculates that is based on the shape and the bounding rectangle. So you have to make sure that those methods are implemented properly. What is QPainter path? That's a good question. Okay, so this is something that you can paint on, just like a QPainter, except that it saves the operation in a data structure so that you can play back those same operations again later. So it has methods like draw line, draw ellipse, draw this, draw that. And when you perform those operations on the painter path, then you can like play it back later on any paint device. Yes? Should we use a QPainter path for what? For what? Undo, redo. Well, if you are, that's a bit of a higher level, undo, redo. So Qt does have something called a Q undo command, which is part of their undo framework. And typically what you would do is you would organize your operations in terms of the Q undo commands and add them to their undo stack. That would be the recommended way of getting undo, redo. But for example, if you needed to attach a piece of data to the undo command, it might be the QPainter path that you'd store with each of those undoable operations. Yeah. So here's the collision detection example where we're looking at the colliding mice again. Oops. So the mouse has a certain shape, and here's the QPainter path. We just add rectangle, and then we return it. So that would be how you'd make a simple rectangle. And in your paint method, you want to set the brush to either dark yellow or red, depending on whether this mouse, in this scene has colliding items. Scene colon items returns a list of items that intersect with your polygon. So items takes a Q polygon, and then you can pass it the points that make up your polygon this way. And since we want scene coordinates, we actually have to call map to scene from our item. And if we wanted to calculate the distance from our mouse to other mice, we could do it this way. Just take the 0, 0 origin and then map from the item coordinates of that item's 0, 0, and that gives you a line, and then you can calculate the distance of that line to figure out how far it is. Animation. So there are many ways to control and to animate these items. In our training material, we talk about 3 ways: the item-based animation, scene-based animation, and then there's Q graphics item animation, which uses a Q timeline. And now, with Qt 4.6, there's an entirely new animation framework, which is supposed to be better than all the previous ones. And I'm still learning it, so I'm not going to say much more about that yet. And if we have time, then I'll show you some examples of the other simpler ways. Performance tuning. There are lots of ways that you can squeeze a little bit more performance out of your application. We'll show you a couple of them. First, there's update modes, and I think this is an answer to one of the first questions that somebody asked me. What is redrawn when your scene changes? So you have choices. Full viewport, redraws everything in your viewport. No viewport update, don't redraw anything unless you explicitly call update yourself. And then we have these degrees in between, such as Only redraw bounding rectangles of changes. Only redraw what has changed. You can mark certain items as, dirty. Or just redraw everything. There are other ways to tweak your application to get a bit better performance. Don't clip your painter. Don't save the painter state, or don't adjust for anti-aliasing. So these are optimization flags on the graphics view. Then you can also set the index method of your graphics scene. And this might be helpful if you have a lot of items that don't move around, because then you can put them into a binary space partitioning tree, which is sort of like a two-dimensional geographical index. If you have dynamic scenes with moving items, well, whenever they move, they have to be removed and then added again to that BSP tree. So there's a bit of overhead there, but then other operations are faster. Other tips, you could use a different paint engine, OpenGL, Direct3D. So you just set the viewport and give it a QGL widget. And then you're using OpenGL underneath. Yes? Can you render a QGL widget within a QGraphics view? I believe the answer is yes. Yeah. Other tips? Avoid curved and dashed lines if you can. Anti-aliasing and alpha blending are expensive. You want your bounding rect to be as small as possible, and the shape should be the simplest reasonable path. And it should be able to run quickly because it gets called a lot. Another tip, if you are going from 4.4 and then you move to 4.5, you might notice degradation in performance. And that's because semi-transparency has been introduced in 4.5. And that does cause some overhead for calculating the opacity. And if your items are not opaque, if you're not using any, if your items are opaque, you're not using any transparency, then you can disable by using item doesn't propagate opacity to children and item ignores parent opacity. So these are new flags that have been introduced that gives you performance if you're creating and scrolling through layouts with millions of opaque items. So in the lab, we're going to extend graphics items and also extend a graphics scene. And we're going to make an initial screen for breakout. So you're going to have a bat, a ball, and a brick item. So those are your three kinds of items. We're going to lay them out on a scene. And in the full version of this course, we even add paddle movement and animation to the ball, as well as collision detection, which is pretty much everything. And you can see the solutions to these labs as well, if you don't know enough about animation yet. How much? Let's see, I started at, it looks like I have 15 minutes left, eh? All right, so now we'll do a bit of animation. Unfortunately, you don't have the handouts for these, so we'll just have to wing it. So let's show you some animations. So here we have a couple of things that are going on at the same time. We have circles that are changing color. We have a square that is rotating and moving. So how do we do all this? Wouldn't you like to know? So there are not three, many ways to control animation. There's item-based, there's scene-based, there's QGraphics item animation, and then there's the 4.6 animation framework. If we're just doing item-based animation, typically what we'll do is create and start a QTimer. Then we inherit from QObject as well as QGraphics item. Why do we need both? Well, the graphics item, as I said before, is not a Q widget. It does not have signals or slots. But we need that here because we need to connect to a timeout signal of a timer to one of our own methods. So here's how we animated the circle, the one that was changing colors. It derives from QObject first because you have to. If you've ever done multiple inheritance with Qt, the first base class has to be QObject, and you cannot multiply inherit from it either. And we have our one slot called onTimeout. When we create the circle, we start the timer. We're saying 10 times a second or 100 milliseconds. We want to call onTimeout. And what does onTimeout do? It just cycles through the hue and calls update. So update here is how we schedule a call to paint without calling it directly, because paint has to be called from the graphics, from the GUI thread. So with scene-based animation, we want to drive the entire scene, perhaps because we're manipulating multiple items at the same time. And so at each step, what happens is we call graphic scene advance, and then it calls advance on each item in turn. And the items have a different signature for advance that takes this integer as parameter, which could be 1 or 0. When 0 comes in, that's your signal to say, prepare to animate. And so you could perform advanced calculations. And then phase 1 is do it. Just a couple things about QTimeline. QTimeline is like a QTimer, but it gives you fancier motion because it has different curve shapes. So it emits a signal periodically like a QTimer. It has these important properties: duration, update interval, frame range. So duration is how long you're going to run this animation for, how many milliseconds between each update, and how many frames or counter IDs you have. Its signal is called frame changed, and that's what you connect to your slot. And the curve shapes that are supported by QTimeline include ease in, ease out, linear, sine, and cosine. And we can see an example of a QTimeline. Here. So this is an ease in out curve. So here we have an example of scene-based animation. So in this we have, and this is from a different example called network, where each item, okay, so the scene connects to just a regular QTimer and calls advance on the scene. And then the scene's advance will call each node item's advance twice, once with a phase of 0 and once with a phase of 1. What kind of application would you want to use this kind of animation on? One example would be the one that comes in network. Examples network. Because here what we have are a lot of items that are all moving at the same time, and they each have to calculate their next position based on certain rules. And they can be based on how much the lines between them have been stretched. So here we calculate how far it's been stretched, and then when it's time to actually do it, we actually set the position to that position. And this gives us smoother animation. Now the third way of animating is with the QGraphics item animation. And there what you do is you create a Q timeline and a graphics item animation object. And then this graphics item animation needs a timeline, so we just set it on that. And the interesting thing about QGraphics item animation is that it interpolates the intermediate steps when all you have to do is specify a couple of endpoints. What do I mean by that? Well, here we have a square that is moving around the screen and also rotating. But we didn't specify the intermediate points between these four corners. All we told it was that at this point it should be in this corner, at this point it should be in this corner, at this point it should be in that corner, and at this point it should be in that corner. How does that work? Here's an example. So the rectangle is what we were seeing rotating around our square. Here's the timeline. We're saying that it's 5 seconds long. It's going to be an infinite loop. That's why we set the loop count to 0. We set the frame range, so that's how many frames per loop. We create the item animation. We tell it which item we want it to animate. We tell the animation what timeline to use. And then we call set position at. And so we can see that the position that we want it to start at, which is at 0, is the same as the one we want it to end at, which is 1. And then the intermediate points are at 25, 50, and 75, are at the other three corners.
So where is the rotation specified?
I knew you were going to ask that. That's not shown on the slide, but it is in the example. So basically we also have set rotation at. Same idea. We give it an angle instead of a point. And you might want to take a look at this class to see what other set types of methods they have. So it's a very handy little class. But like I said, the 4.6 animation framework might make all of these obsolete. So, three kinds of animation that we've seen: item-based, scene-based, and item animation. And in all of them, we're using either a QTimer or a QTimeline. And now, to the main summary. What we've learned: overview of the graphics framework, coordinates, transformations, how to extend our items, how to handle events, drawing graphic scenes, items, collision detection, and performance tuning. So, now I'm at the end of my talk. If you have any more questions, you can feel free to ask. I think we got another 5 minutes or so.
Back to your hello world example, you didn't specify any placement coordinates for those objects in the scene.
They were item coordinates, which were relative to the item, correct. Each item has its own coordinate system. What's your question? Well, by default, it's just in the middle at 0, 0. How big to make it? Well, if we look at that hello world again, How does the scene know to which? Okay, first of all, I don't know which box you're talking about, because what we're doing is we're just drawing an ellipse, and then we're drawing a hello world inside.
Okay, Alan, maybe I can answer that because this has been asked of me a couple of times. What's happening there is both the ellipse and the text have a position of 0, 0, 0, and they don't fill the view because it's -10, -10, 120 by 50, which is smaller than the size of the view. And so when the scene is smaller than the view will automatically center it. So that is why it's being centered. Now, if the scene was bigger than the view, then you'd have scroll bars up there. So by default, if it's smaller, it's going to try to center it.
Oh yeah, and the view knows how big it needs to be based on those shape and bounding rect already. So it just adds some extra margins to make it look the right size. Any other questions?
When you talked about, multiple inheritance with QObject and QGraphics item, why did you say you need to specify QObject first?
That is a limitation of the way that mock works, the meta object compiler. It generates code and it just makes the assumption that the first base class is QObject.
Is there a separate duplicate hierarchy for graphics items since they're not widgets? Kind of making, since graphic items are not widgets, is there a separate hierarchy of those to kind of, like you mentioned, it's used in KD4. Did they make all those widgets that exist on the widget side, or how does it work?
Right. So another topic that we talked about in the full version of this course, which I didn't really mention, was that you can put any widget into a graphics scene thanks to the QGraphics proxy widget. I think it might be briefly mentioned, but yeah. So the QGraphics proxy widget enables you to take any widget that you've written and stick it in your scene.
I guess the confusing part was that any widget that I wrote or existing widget, does it need to be customized? In other words, does the widget need to be customized?
Both. So your widgets, other people's widgets, anything derived from QWidget.
So my question is, how do you make the decision whether to use a Q main window and put graphics view or graphics item, I guess graphics view and then graphics items inside it, or you use a graphics view and embed widgets inside it? So what are the considerations in making that kind of a decision?
Well, first of all, you're probably always going to have a main window around whatever it is in the center.
Okay.
And the QGraphics proxy widget, when you put it into a graphics view, isn't going to look quite as nice as if it was painted directly on your screen, because it does have to go through a bit of transformations. So it's not going to look quite as nice. So I would recommend only putting widgets into your scene that have to be in your scene, but having your main UI use proper widgets.
Okay, so we use graphics view if we don't need a lot of widgets, like built-in widgets. If we need a lot of widgets for the UI or application, then it's better to just use the widgets and use graphics view only if we need it. Is that true?
Well, there are other situations where you might want to create special GUI components that are just graphics items of their own right, and then you can make them react to user clicks and other interactions just like any other GUI component. So that's yet another approach. Okay. Which is best for your particular application? It's something that I'd actually have to look at more closely in order to answer.
if your application just uses a lot of widgets that are already available, like combo boxes, but you just need a different look and feel, then it's better to just use those widgets and use styles, correct?
Probably, yeah.
Okay.
Any other questions?
Classification to inherit from queue object first is only limited to queue object, or there are other classes in which I should order the inheritance?
Queue object is the only one that's like an imposed restriction on you and the way that you program. And that's only because of the way that it has to be pre-processed by the meta object compiler, mock. So you don't have to worry about that for the other classes. Of course, you still have to worry about multiple inheritance and whether you're inheriting from the same base class more than once. And we don't use virtual base classes very much in Qt.
Thanks.
All right. I think that's all the questions then. And I'm out of time. So thank you very much.